general relativity, step by step. I've been talking about the stress energy tensor here, this T alpha beta, for some time, but there's more to be said about it. So I'm just going to give you the original or the easy to work with formula: rho plus b u alpha u beta plus p g alpha beta. I might have implied, in fact I think I said earlier, that that was only true for flat space, but it's not. It's true for any space at all, so long as you have your fundamental tensor here and not just the G for flat space. Okay, so I'm just going to consider the two. Components, the t and the x component. So I'm just going to work in a one-dimensional world here, and I'm going to specify that my 4 vector here is gamma and gamma u. I guess I could put zeros here as well, but I'm just going to suppress those for the moment, and I'm just going to evaluate this thing here directly. T alpha beta equals p plus rho. Observe I'm still setting c equals 1 here. U alpha u beta plus p g alpha beta. And I'm going to work in flat space where g alpha beta is just that. Of course, I'm suppressing the other coordinates here. So that's my version of u here. And so what does that turn into? So I can say that t 0, 0 equals p plus rho u0 plus p g0 0, which is this term here. And so that's the 0 term of u, and that's the 1 term here, 0 term being time, I guess. P plus rho gamma squared, gamma equals 1 over root 1 minus u squared, plus p times minus 1. So it's equal to rho gamma squared plus p gamma squared minus 1. What about the other terms here? So what have we got here? We've got some rather peculiar terms here. We've got this term here, which is obviously a kinetic energy term. Well, okay, I say kinetic energy term. Well, it is what it is. It's just rho gamma squared. Plus this rather peculiar thing here. Well, let's evaluate it. Well, let's evaluate it. So gamma equals 1 over root 1 minus u squared. So gamma squared is 1 over 1 minus u squared, which equals 1 plus u squared plus order u to the 4, which we can ignore. So I'll just keep that term there, and we've got rho gamma squared plus p times 1 plus u squared minus 1 plus higher order terms, I guess. Yep, equals rho gamma squared plus p u squared plus higher order terms. Yeah, of course, u, you've got to remember, is your normal classical velocity over the speed of light. So if I put the units back in, we've got rho gamma squared plus, and of course p in normal units is p over c squared. So it's p u squared over c to the 4 if I want to put the units in. So this term is a very, very, very small correction. I don't really have a classical gloss on this term. It's just, it is what it is. It's a small correction term that you get when you put the transformation laws in. Okay, so that's t0, 0. Let's just pinch in a little bit and let's work out what t1, 1 is. Well, that's again p plus rho times gamma u plus p times plus 1, I guess, in this time. These terms here being the relative components, or the space component of your 4 velocity here. Oops, I meant to pinch in. Equals p plus rho gamma squared u squared plus p. Well, again, it is what it is. So that's it there. So that's the momentum density of your fluid. Yeah, so it's got p, it's got a rho term in there which creates its own density, gamma squared u squared. So it's a momentum density. And there's one other term here, which is the t0, 1 term, which is p plus rho gamma u, no, that's a gamma, plus p times 0. This is the off-diagonal element, and if I look at the formula here, the general formula, we'll see that when I put alpha not equal to beta, we're off the diagonal, and so certainly in flat space we've got a 0 term there. Equals gamma squared u p plus rho u. No, I've got u already. Yeah, that's right. Okay. So what does that correspond to? That corresponds to either a momentum density term in the u direction or a energy flux in the u direction, both of which are the same thing. Okay, so we can play with this formula and substitute various bits and pieces into it, and I'm going to do the same task in a slightly different way in the next screencast. Okay, I'm going to stop there. Stop.